A tugboat pulls two barges to the right. The front barge has mass 2.00 times 10 to the third kilograms, and the rear barge has mass 3.00 times 10 to the third kilograms. A negligible mass cable connects them. The tugboat exerts 29,000 newtons. Water resistance is 6,500 newtons on the front barge and 10,000 newtons on the rear barge. We need the common acceleration and the tension in the connecting cable. Use the full Newton's second law strategy. First, draw a free body diagram. Second, define coordinate axes. Third, decompose forces into components. Fourth, write Newton's second law equations. We will complete that strategy for the two barges separately. This method gives both requested quantities and remains useful when a problem becomes more complicated. Only after the complete solution will we compare it with whole system reasoning. Draw one free body diagram for each barge. On the front barge, the tugboat's applied force points right. Cable tension and water resistance both point left. The rear barge is pulled right by the cable tension and left by water resistance. Each barge also has weight downward and a buoyant force upward. Those vertical forces balance, but showing them makes the free body diagrams complete. Now check the cable interactions. The cable pulls the rear barge right and the front barge left. These two displayed forces are not a Newton's third law pair with each other. Each one's third law partner is a barge pulling on the cable. Why may we use one symbol, T, for both magnitudes? The cable has negligible mass, so a substantial net force would imply an unbounded acceleration of the cable. Its end forces therefore balance, making the tension magnitude the same throughout this cable. Choose positive X to the right and positive Y upward for both barges. Every force already lies on one of these axes, so step 3 requires no trigonometric decomposition. The connecting cable keeps both barges at the same horizontal acceleration. Vertically, each buoyant force balances the corresponding weight. Those equations are a useful check of the complete diagrams, but none of the requested quantities depends on them, so the remaining algebra will use only the horizontal equations. For the front barge, read the horizontal forces from the diagram. The applied force points positive, while tension and water resistance point negative. Therefore, F minus T minus F1 equals M1A. For the rear barge, tension points positive and water resistance points negative. Thus, T minus F2 equals M2A. The applied force does not act directly on the rear barge. We now have two equations for the two unknowns, acceleration and tension. Use substitution to solve the pair consistently. From the rear barge equation, tension equals M2A plus F2. Substitute that entire expression for T in the front barge equation. After collecting terms, F minus F1 minus F2 equals the combined mass times A. Dividing by M1 plus M2 gives the acceleration. Adding the two original equations would eliminate tension more quickly, but substitution makes the connection between the equations explicit. Using the values in thousands gives 29 minus 6.5 minus 10.0 divided by 2.00 plus 3.00. The acceleration is 2.5 meters per second squared to the right. Now return to the rear barge equation. Tension equals M2A plus F2, which gives 17.5 times 10 to the third newtons. Substituting that tension into the front barge equation reproduces M1A, so both individual force diagrams are consistent with the same acceleration. After completing the individual object analysis, we can recognize a shortcut for acceleration. Enclose both barges in one system boundary. Tension is now an internal force, so the two cable forces cancel when the barge equations are added. The external horizontal force is F minus F1 minus F2, and the system mass is M1 plus M2. This reproduces the acceleration efficiently. But because tension is internal to this larger system, the shortcut cannot determine its value. We still need an individual barge equation for that. The barges accelerate rightward at 2.5 meters per second squared. The connecting cable tension is 17.5 times 10 to the third newtons. The primary method is the full four-step Newton's second law strategy. Draw a free body diagram, define coordinate axes, decompose forces into components, and write Newton's second law equations. Whole system reasoning is a useful conceptual shortcut after that analysis. It exposes why internal tension cancels when finding acceleration, while also showing why the shortcut alone cannot answer the question about tension.